Okay, basically it's a valley whose bottom is completely flat. So that means actually we have a degenerate critical point. It's called degenerate because there's a direction in which nothing happens, and in fact you have critical points everywhere along the y-axis. Okay, so now whether the square that we have is x or something else, namely x plus b over 2ay, it doesn't matter. I mean, it will still get this degenerate behavior, but there's a direction in which nothing happens because we just have the square of one quantity. I'm sure that 300 students means 300 different ringtones, but I'm not eager to hear all of them. Thanks. Okay. So this is what's called the degenerate critical point. And okay. So basically, we'll leave it here. We won't actually try to figure out further what happens. And the reason for that is that when you have an actual function, a general function, not just one that's quadratic like this, then there will actually be other terms, maybe involving higher powers, maybe x cubed or y cubed or things like that. And then they will mess up what happens in this valley. And it's a situation where we won't be able actually to tell automatically, just by looking at second derivatives, what happens. See, for example, in a function of one variable, if you have just the function of one variable, say f of x equals x to the 5, well, if you try to decide what type of point the origin is, you're going to take the second derivative, it will be 0, and then you can conclude. Because things depend on higher order derivatives. So we just won't like that case. We just won't try to figure out what's going on here. Now, the last situation is if 4ac minus b squared is positive. So then that means that actually we've written things, the big bracket up there is a sum of two squares. Okay? So that means that we've written w as 1 over 4a times plus something squared plus something else squared. Okay? So these guys have the same sign, and that means that this term here will always be greater or equal to 0. And so that means that we should have either a maximum or a minimum. How do we decide which one it is? Well, we look at the sign of a, exactly. Okay? So there's two subcases. One is if a is positive, then this quantity overall will always be non-negative, and that means we have a minimum. Okay? And if a is negative, on the other hand, so that means that we multiply this positive quantity by a negative number, we get something that's always negative, so 0 is actually the maximum. Okay? Is that clear for everyone? Yes?
In your second case, you said that it did not depend on y because for ac minus b squared equals 0.
So yeah, I said in the example w equals x squared, it doesn't depend on y. If I have, so the more general situation is w equals some constant, well, I guess it's a times x plus b over 2a times y squared. So it does depend on x and on y, but it only depends on this combination. Okay, so if I choose to move in somehow the perpendicular direction, in the direction where this remains constant, so maybe if I set x equals minus b over 2ay, then this remains 0 all the time. So there's a degenerate direction in which I stay at the minimum or maximum or whatever it is that I have. Okay, so that's why it's called degenerate. There's a direction in which nothing happens. Okay? Yes?
You said this is called the second derivative test. Are we going to take the actual derivative?
Yes, yeah, so that's a very good question. So I said it's going to be the second derivative test. Why do we not have derivatives yet? Well, that's because I've been looking at this special example where we have a function like this, and so I don't actually need to take derivatives yet. But that's because a, b, and c will be the second derivatives of the function, actually 2a, b, and 2c. So now we are going to go to a general function, and there, instead of having these coefficients a, b, and c given to us, we'll have to compute them as second derivatives. Okay? So here I'm basically setting the stage for what will be the actual criterion we'll use using second derivatives. Yes? So, yes, so when you have a degenerate critical point, it could be a degenerate minimum or a degenerate maximum, depending on the sign of A. But in general, once you start having more complicated functions, you don't really know what will happen anymore. It could also be a degenerate saddle and so on. So we won't really be able to tell. Yes? It is possible to have a degenerate saddle point. For example, if I give you x cubed plus y cubed, you can convince yourself that if you take x and y to be negative, it will be negative. If x and y are positive, it's positive. And it has a very degenerate critical point at the origin. So that's a degenerate saddle point. We don't see it here because that doesn't happen if you have only quadratic terms like that. You need to have higher order terms to see it happen. Okay. So let's continue. Oh, before we continue, let's see. I wanted to point out one small thing. So here we have this magic quantity 4ac minus b squared. You've probably seen that before in your life. Yeah, it looks like the quadratic formula, except that one involves b squared minus 4ac, but that's really the same thing. Okay, so let's see, where does the quadratic formula come in here? Well, let me write things differently. Okay, so we've manipulated things and gotten to a conclusion. But let me just do a different manipulation. And write this now instead as y squared times a times x over y squared plus b x over y plus c. Okay, see, that's the same thing that I had before. Right? Well, so now this quantity here is always non-negative. What about this one? Well, of course, this one depends on x over y. It means it depends on which direction you're going to move away from the origin, which ratio between x and y you will consider. But I claim there's two situations. One is, so let's try to reformulate things. So if the discriminant here is positive,